In this video, we're going to be looking at Chapter 3, Inductive and Abductive Arguments, from Elliott Sober's book, Core Questions in Philosophy. This is from pages 24 to 34 of our reading for today. Abduction is also known as inference to the best explanation. An example of an abductive inference from the history of science is from Gregor Mendel. Mendel is known as the father of genetics, and he observed regular variations while breeding different types of pea plants and offered genes, which he called elements, as an explanation. I remember this being in one of my history books, I think, when I was in elementary school, so maybe you remember this too, the pictures of the pea plants, and Mendel positing genes as the explanation for the differences. Now, Mendel's theory of the gene went beyond observations available to him. He never saw a gene, although we eventually were able to with microscopes, but he didn't have microscopes when he was positing the gene. But his theory postulated the existence of genes. If Mendel had made an inductive inference, on the other hand, he simply would have claimed that the observed results of the experiment he ran would also occur anywhere that they were carried out in the world. However, he didn't simply claim that the experiment could be replicated. Instead, his inference drew a conclusion about why the results occurred. Mendel's inference drew a conclusion concerning something he did not see, genes, based on the premises that described what he did see, the result of his breeding experiments. Let's look at Mendel's inference more carefully. Experimental crosses in the pea plants were observed to exhibit such and such results, premise 1. So the conclusion. So there are genes, and they obey laws L. Notice that this is not a deductively valid argument. Remember, you can't validly deduce a theory from a set of observations. But why not? The previous argument attempts to infer a theory about the case from the observations of its effects. However, there are lots of possible causes that might have been responsible for the observed effect. Here's a similar argument. The argument is deductively invalid for the same reason as this argument is invalid. A pistol with an M on the handle, an El Supremo cigar butt, and a size 12 footprint were found next to the murder victim. So Moriarty is the murderer. This is some reasoning from Sherlock Holmes. Notice that although Moriarty may be the most plausible suspect, the clues in themselves don't absolutely guarantee that he must be the murderer. There are other explanations, right? Remember that deductive arguments give us absolute certainty if the premises are true. Okay, let's try this. We might think that if a set of observations doesn't deductively imply a theory, then perhaps the reverse is true, and the theory implies the predictions. This would mean that if the predictions come true, then the theory is probably true. But here's a spoiler. This isn't going to work. But let's give it a try. Premise 1. If there are genes and they obey laws L, then experimental crosses in the pea plants should exhibit such and such results. Experimental crosses in the pea plants were observed to exhibit such and such results. So there are genes and they obey laws L. Now, if you recall, this is the fallacy of affirming the consequent, as it is shown here in our old friend, an argument from the previous section. If Jones lives in Wisconsin, then Jones lives in the USA. Jones lives in the USA, so Jones lives in Wisconsin. Remember, this argument is invalid. But note that this method applied by scientists isn't wrong. Scientists often test their theories by seeing whether the predictions made by the theories come true. There isn't anything wrong with this. The point, however, is that the truth of the theory doesn't follow deductively from the truth of the prediction. Scientists are reasoning non-deductively when they decide that a theory is plausible because its predictions have come true. Successful prediction isn't absolutely conclusive proof that a scientific theory is true. However, if the prediction entailed by Mendel's theory had come out false, that would have allowed him to deduce that the theory is mistaken. Now, what's going on here? Notice that this is a deductively valid argument. If there are genes and they obey law L, then experimental crosses in the pea plants should exhibit such and such results. Experimental crosses in pea plants don't exhibit such and such results. So, it's false that there are genes and they obey laws L. In other words, a failed prediction is conclusive proof that the theory implying the prediction is false. So let's look at this speaking generally. So we're going to use a couple of items here. T equals the theory that we're considering, and P is the prediction. So if T, then P, so the prediction, so T, remember that this one is invalid. But this, if T, then P, not P, so not T, is valid. This means that it's possible to reject a theory just on the basis of the false prediction it's making using a deductively valid argument. But it isn't possible to accept a theory just on the basis of the true predictions it makes using a deductively valid argument. But how do scientists ever interpret observations as providing strong evidence in favor of the explanations that they're considering? This must involve a non-deductive inference, but what are the rules that govern such inferences? Yeah, let's try this out. Maybe all we need to say is that a theory is made highly probable or plausible when a prediction it makes comes true. Here's another spoiler. This isn't going to work. But let's investigate why. We're going to look at an example of a weightlifter. You go to a gym, and someone tells you that they're an Olympic weightlifter. Remember when we could go to gyms? We're back there. So you reason that if this person were an Olympic weightlifter, he should be able to pick up your hat. So you give him your hat, and he lifts it without any difficulty. Notice that I made a prediction and it came true. But is this strong evidence that this fella is an Olympic weightlifter? Of course not. What should I be looking for? What should you look for if you want to test the hypothesis that this man is an Olympic weightlifter? You want to identify something that you would expect to be true if he were an Olympic weightlifter, but that you would expect not to be true if he were not an Olympic weightlifter. Let's suppose that Olympic weightlifters of this man's weight can almost always lift 400 pounds at some particular kind of lift, and that people who are not Olympic weightlifters can't. If this is true, then it would mean that his ability to lift 400 pounds at this particular lift would be strong evidence that he's an Olympic weightlifter. And this brings us to the surprise principle. The surprise principle says that an observation O strongly supports a hypothesis H1 over hypothesis H2 if both the following conditions are satisfied, but not otherwise. Condition 1, if H1 were true, O is to be expected, and condition 2, if H2 were true, O would have been unexpected. Okay, now let's look at a couple of things with regard to the weightlifter here. So the observation is the man lifting 400 pounds, and H1 is this man is an Olympic weightlifter, right? So this is what we would expect to be true given our observation. And then H2, we would expect not to be true. This man is not an Olympic weightlifter if he can't lift 400 pounds. Okay, so here is a challenge to this. You see someone crossing campus with an armload of philosophy books. So here's a couple of hypotheses. The person is a philosophy major, and hypothesis 2. The person is an engineering major. So according to the surprise principle, H1 is favored over H2 because of your observation of seeing them cross campus with an armload of philosophy books. You would expect a philosophy major to be crossing campus with an armload of philosophy books, while you would not expect an engineering major to be crossing campus with an armload of philosophy books. But what about hypothesis 3? The person isn't a student, but is in the business of buying and selling textbooks. Although your observation discriminates between hypothesis 1 and hypothesis 2, it doesn't discriminate between hypothesis 1 and hypothesis 3. This brings out an important fact about how the surprise principle applies to abductive inferences. If you want to know whether an observation strongly supports a hypothesis, ask yourself what the alternative hypotheses are. For an observation to strongly support a hypothesis is for it to strongly favor that hypothesis over the others which it competes with. Keep in mind, successful predictions don't automatically provide strong evidence. The surprise principle gives advice on what a hypothesis must do if it's to be strongly supported and by the predictions it makes. First, the hypothesis shouldn't make false predictions. And second, among the true predictions the hypothesis makes, there should be predictions we would expect not to come true if the hypothesis were false. Okay, now this brings up the possibility of a fallacy known as the only game in town fallacy. Imagine that you and I are sitting in a cabin in the woods. We hear a strange rumbling in the attic, and you ask, what could that be? I reply, oh, that's the sound of gremlins bowling in the attic. So you're very sensible, and you reply to me, I don't think that there are gremlins in the attic. So I challenge you to give me a more plausible explanation. You reply, gosh, I don't really have one. I just think your story is implausible. So I reply, look, my story's true. And if it were, it would explain why we just heard those strange noises. If you don't want to accept my explanation, you must produce a more plausible explanation of your own. If you can't, you have to accept my explanation. Now notice that this reasoning commits an abductive fallacy that we're going to call the only game in town fallacy. The fact that you can't think of a more plausible explanation of the noises doesn't oblige you to accept the story I constructed. There is an alternative, which is simply to admit that the noises are something you don't know how to explain. All right, so this has been an overview of abductive arguments, also called inference to the best explanation.